Hello, I'm Ann Hanks from PASCO Scientific.
And my name is Brett Sackett. I am Ann's partner in physics.
Partner in crime. We're going to be talking about the Educational Spectrophotometer. And this is a device that we invented a long time ago that takes the guts of a regular spectrometer, optical spectrometer, and opens it up so that the students can see the paths of the light, where the light's going, how it ends up showing you the spectrum. We're going to be looking at the atomic spectra of Mercury, simply because Mercury is really bright source, so it makes it easy to show in this lighting.
And it has beautiful spectral lines.
It does have nice lines.
We love Mercury.
Yeah. So the way this educational spectrophotometer works is it uses a high sensitivity light sensor and a rotary motion sensor, which you should show on this side.
Yeah. And so it's probably important to point out, if you're familiar with PASCO products, you know that we have some wireless sensors, we have blue sensors that we call Passport, and then we have some sensors in black cases that we call Science Workshop. And the difference is the Science Workshop sensors are analog, and so you could use the Science Workshop sensors for this. And the benefit of the analog sensors is if you want to adjust the gain, is that we allow you to do that on the sensor and in the software. This rotary motion sensor here has our highest resolution on a rotary motion sensor. This has 4,000 divisions per revolution, so that allows us to measure the angles very accurately.
Which is why my preference is to use this rotary motion sensor in blue and actually use the black high sensitivity light sensor, because I can up the gain so well on it.
Right. If you have spectral lines that are very weak, the other sensor allows you to crank the gain up. Another thing to point out is that this is really a part of our optics systems. And so these optic benches and components allow you to do basic geometric optics, lenses, telescopes, the usual optics experiments you can do. And then from there you can get accessories and build out into more advanced experiments.
So going from the light source in, we have a Mercury light source here. It's actually the one that we use for our photoelectric effect as well. And it's very bright. You should not look directly into it.
And the case is very hot.
Yes, the case is pretty hot, so once you've got it set up, you don't want to be grabbing it. Then there's a collimating slits here, which I didn't bring an extra one of. I actually have them screwed down to the track just to make things more stable. But the collimating slits just allows you to choose between 5 different slit sizes. And depending on how bright your source is, in this case, I'm on the smallest slit size because the Mercury is extremely bright. So that allows me to get very fine lines and yet still be able to see it. Now, if you're doing something like hydrogen tube, then that is going to need you to open up to a 5 probably, or at least a 4. These spectral tubes that we have are slightly different height than this Mercury tube. And we have rod stands that slip into the track and allow you to elevate the track to whatever the center is on the tube. So you can have different height sources and still be able to see them all. Yeah, I gotta remember to put that back. Now,
We're gonna have to refocus that.
yeah, that's the after the collimating slits, there's a collimating lens, which has a focal length of about 10 centimeters, and it's supposed to be focused on the slit. Now, I don't know, I just moved the slits, so I'm gonna check, and you have to put your head down in here and look over the diffraction grating through to the slits and see if it's focused. I'm trying not to look at the mercury source straight on. That looks pretty good.
All right.
And then,
And that's one of the setup tricks, is sighting the collimating lens just over the diffraction grating.
yeah, and then once the rays come out of the collimating lens, they are parallel, and then they go through the diffraction grating. Excuse me. The diffraction grating is held on magnetically, and it's on a, where do you get that one?
This one?
Yeah. It's on the turntable,
Yeah.
and the turntable is held on magnetically also. And just a quick tip, if your apparatus gets old like ours has, you can put a little bit of silicone spray on the magnet and it will make it slip easier. This one is actually pretty sticky right now.
So this platform here is used in a number of different experiments as a way to measure the angle. Look at the light intensity as a function of the angle, or you can do a calculation to what the wavelength is. And so you'll see this appear again in a bit when we do the black body experiment. And so it allows you to attach optical components on top of the table so that you can rotate without rotating whatever you've attached to the top. This is a spring-loaded door here, and that's where we mount the rotary motion sensor.
One important thing about when placing this, the grating holder, you don't want to screw it all the way down.
Right.
Because if you do, it will stop the whole thing from turning. It'll just all turn together.
Right.
So there's a set screw. It's actually a wing nut that goes underneath that allows you to hold it in place at a certain angle. You want that to be perpendicular to the light beams that are coming through. And then the most important thing is that on the grating, on the magnet side, is where the actual grating is laid onto the glass. And so one side has a big thick piece of glass on it, the other has the grating exposed. You want that exposed grating to be away from the light. So, and then it's that part of the grating should be centered on this table so that when you rotate it, you're rotating about the center of the grating, not the center of the glass. Mm-hmm. And you want the light to go through the glass first so that it goes straight through the glass and then gets diffracted through the grating so that you're measuring the actual diffraction angle rather than measuring that plus the glass.
Right. Let's talk about the pinion too.
Yeah, while we're at it, we'll do that. So, as Brett was saying, go ahead and show them the flap on there.
Yeah, so here's the door, or the spring-loaded door that the rotary motion sensor attaches to, and this spring holds the rotary motion sensor against the edge of the rotating plate.
Now, I want you to notice, and we're very proud of this, there's screw storage here for the screws that attach the rotary motion sensor. And the rotary motion sensor has a rod clamp on it that you may have to move from the end to the side, or you don't need it at all. But there's an important step in setting this up, because there's a pinion here that you're slipping over the rotary motion sensor shaft, and then you tighten that on. There's two ways to put that pinion on, because for other experiments, you're not using this, you're using the wider one. When you're using this pin, the smaller pin, you put the rotary motion sensor in the lower holes, and then if you want to use the other pin for less fine experiments, you put it in the upper holes here. But important to making this work is that as you rotate this platform around, it rubs on that pin, and it has to be sure to rub on it at all times and doesn't lose traction. It does quite well because this really is a round plate. And as I turn this around 360 degrees, the pinion turns 60 times. So it gives us a mechanical advantage and allows us to measure smaller angles. The key to doing this right is that you pull, once you've got it on there, you pull it away from the table and you loosen the screws and you tip and pull the rotary motion sensor toward the hinge and then tighten it up so that when it flops back, it's in good contact with it. Otherwise, it could be too loose. Mm-hmm. But once you've got that set up, then it all works perfectly.
Right on. And so then attached to the top of the plate is an armature. You can see this arm extending out.
Let's go back.
And that's how we've attached the aperture bracket. There's another focusing lens here, an aperture bracket, and then the high sensitivity light sensor.
Yeah, so after you have the diffraction pattern, there's a focusing lens which you just focus right on to the screen here to focus the lines and make sure that they're clear. And then we have this aperture bracket which has this white screen on it so that you can see the
spectral line.
The spectral lines. I was just thinking that I didn't bring my piece of paper with me, but turns out
we're getting a piece of paper.
Yeah, we're getting a piece of paper. Oh, thank you. It turns out that it's smart to put a piece of paper in front of it and look at the lines, and you're not going to be able to see this with the lights on like this, but because the paper will fluoresce, there's a UV line in Mercury spectrum that you can see, but you won't see it here. You will see it when we do the scan. And if you put a piece of paper in there, since the paper fluoresces in the UV, then you see a bluish looking line there before the first purplish looking line, or violet, as they say in the technical world. And so it's just a good way of showing students why they're getting a peak before the visible part. This mask in front of the light sensor has slits also, just so that you can very finely look at the pattern. The slit I have on the very narrowest this time, because as I said, the mercury's quite bright, and so we can afford to do that. But you may not be able to always afford that because you might need to get more light through. The sensor itself has buttons on the side of it, at least the Passport one does. And it's made for idiots, so it shows, I'm sorry, but I thought it was bad. It shows a candle, a light bulb, and a sun. And so for this particular experiment, I just put it on the light bulb because the middle range is good enough and it doesn't blow out the central maximum. But if you're looking at something quite a bit much dimmer, you're going to be putting it on the candle setting. And usually you don't use the sun setting in this case, unless you take this out in the sun to look at the spectrum of the sun.
Which you can.
Which is so cool. And then you can stick a leaf in here between the light sensor and the slit. And a green leaf will have chlorophyll absorption bands. And so you'll be able to see the absorption bands. And I know that the biologists go to a lot of trouble making up formulas, liquids, and putting cuvettes in there and stuff. But I found out it works to just put the leaf in. Okay, so line this back up here so you can see the light.
And you'll also notice there's a blue cable here.
Yes.
Which is our grounding cable. And we've got it connected to a ground on the 850 here.
Because as it turns out, the optics bench being metal and everything makes a wonderful antenna for noise. And so we ground everything. In fact, the light sensor is grounded to the apparatus. We purposely have in the screw that you're putting the tightening it on with, that nut is electrically connected to the circuit inside so that the grounding is complete. So that will get rid of a lot of noise. And it's absolutely necessary when you're doing the hydrogen spectrum. And if you do everything carefully, you can see all 5 lines in hydrogen.
Okay.
So looking at the workbook, this is a workbook that steps you through the theory and the setup and tells you how to set everything up. But the one thing that's good about this is it has settings, suggested settings in here. For instance, for the hydrogen setting, it says to put the light sensor on 0, 1, which is the most sensitive, and then the collimating slit on 3, and the light sensor slit on 2. And so it just gives you an idea where to start and to get the best scan. The grading is a certain number of lines it's 600 lines per millimeter. Of course, that's not really known perfectly. So you do need to calibrate the grading if you want to get exact results. And you do that by choosing a known line. We used to use sodium for that, but because sodium lamps have gone out of use in parking lots and every place else, we no longer can make our sodium lamp. So I used one of the lines in the Helium Spectrum as a known to find out what the grading spacing is. So here's an example of the helium spectrum, and you can see that in this particular case, I actually was maxing out the light sensor on this scale slightly. this is the central maximum that goes straight through. And then it's extremely bright. So it's oftentimes gets maxed out. But as long as you can find the center of that, or if you want, you can scan both sides and look at both sides of the spectrum and go from a green line over here to a green line over here and avoid the center line. But the spectrum itself has some pretty bright lines. This is for helium. The yellow line's quite bright. And then it's got some pretty dim lines too. And you can see that there's some noise down at the bottom here where we are not, we're getting down into the noise level, but we're still able to see the peaks. And you can pick those out and measure the angle to those peaks. And from that, you can determine what the wavelength of each of the lines are. And the helium spectrum also has a UV line that's quite strong. Do you want to show a scan?
Yeah, let's collect some data.
Okay. Is this on the middle here? It is. Okay.
Yep.
Let's just pick the Mercury spectrum here. And I'm going to push record. And you do have to, what you want to do is start to just to one side so that your slit is just to one side of the central maximum. And this is a blazed grating, which means that it throws light more one way than it does the other. So it's quite bright on one side and not as bright on the other side. So that has a disadvantage if you're trying to measure from one side to the other and then dividing by 2 to get the angle. But it also makes it so much brighter on the one side that it makes it easy to pick up the lines. So in this case, that is this side. And so I'm going to start on the side that is just opposite that across the central maximum. And then I push record. You have to move this very slowly because the light sensor takes time to react. And in the central maximum, it's not too important. But there is, Brett, we push the auto scale on that?
Yeah. Where's the mouse? There we go. There we go.
Well, that looks terrible. What's going on here? Well, let's keep going. We'll see. You can just skim through the part where there aren't any lines. And then when you get up close, oh, well, the lights are on. That's no wonder.
It does work better in the dark.
It works better if you turn the blasting lights off. Anyway, but as you go across the lines, you slow down and very carefully move it.
Should you go and turn it on?
Go ahead.
Try it.
It will get better.
There's just a sudden shift in the data.
Oh, jeez. Oh, that's lovely.
We've lowered the light floor.
Yeah. There's where all the extra light was coming from.
Yeah.
That's kind of ridiculous, isn't it?
Let's try again.
Okay.
Let's try that.
Go
again.
back. Oh.
All right. Can you pick up the spectral lines?
Absolutely.
Okay, cool.
Okay.
We'll do it in darkness. There we go.
There's a little reflection there that you get off of it. The lenses here have anti-reflective coatings on them, which is why you shouldn't scrub them with a brush or anything. But you do need to have anti-reflective coatings in order to keep all these reflections down between pieces of glass. Now, this actually is a pretty old spectrometer. In fact, it could be 30 years old.
It's one of the originals.
Yeah, it was the only thing I could find. So it is a little sticky, which is, I should have cleaned it up beforehand. Okay, so that's it. And then, of course, you would normally blow this up quite a bit so that you can see it. I'm going to change the data appearance to being thicker so you can see it a little better. And I left the data points on, although you wouldn't have to do that. It does show you how many data points you're getting per peak. The peaks are quite well defined here. So, and it's easy to turn on the coordinates tool, and the coordinate tool will attract to the peaks. So you can just drop it and it will go to the peak. And then
it's a data point attractor.
Yes. And then you can turn on the delta tool and you can go back to where the central maximum was. Here, grab my delta tool. Can't see with my glasses. Okay, and you go back and measure to the central maximum, and then you can get the angle out to that maximum. Yeah. Now, you can also use annotations then, like I did in the previous lab, and stick an annotation on there and say, this is the blue line, you know, whatever. And you can put in what your wavelength is that you get. This is a plot of light intensity versus angle. You can change that axis down here to being a wavelength, and you just can use the calculator to put in the what the wavelength is, the equation for the wavelength according to the angle. And so, you know, it goes as the sine of the angle. And this is for the first order, so m is equal to 1. So you can calculate that, and you could actually have this plot out versus wavelength if you'd like. You have to subtract off where your 0 started. But generally, in a real spectrometer that you're looking through, you're just measuring the angle off of it. Mm-hmm. And so people normally just take that angle and then they put it into the equation to figure out what the wavelength is. You can also do the second order of Mercury, and I'm not going to try here, but out in the second order, they're spread apart. There's more dispersion. So the yellow line or orange line in Mercury is a doublet. And although you can't see the doublet in the first order, in the second order, the peaks are just far enough apart that you can see them and measure them. Mm-hmm. And then you can see the difference. The educational spectrophotometer is meant for education, and it's not a precise instrument. In fact, if you try to look at sodium, and the doublet in sodium, you won't see it even in the second order. And that's just the fact that this is not that good of a resolution. It's good enough to teach the concepts. And I like having it all open so you actually are seeing the spectrum as you're scanning it. And that really ties in for the student then. Oh, hey, this is the green line, guys, that we're doing right here. So, you know, you look at the screen and you can see the green line coming in.
Right. But that's what we do in physics, is instead of just using a fancy CCD-based spectrometer and getting the spectrum, we're really interested.
We work hard at it.
We work hard at it, and we're really interested in teaching the concepts behind how is that spectrum produced by understanding the optical paths and the diffraction grading.
Yeah. You can also calibrate your angle by moving this through a known angle. The angles are marked up here, and so you can look at the indicator, put that on 50 degrees, and then just start recording, and then move through to 50 degrees on the other side, and then you know that you've theoretically gone 100 degrees.
And I think also it's important to point out that when you put this pinion on the rotary motion sensor, there's a calculation in the file
Yes.
that converts the motion of the rotary motion sensor based on the radius of the pinion to get you,
That's 60 to 1.
the ratio.
Yeah.
Yeah.
Otherwise, it'll, if you just look at plain old angle coming out of the rotary motion sensor, it's going to think it's gone through many
Right.
turns, and you'll have a huge number.
Yeah.
But you really should be dividing by 60. So, any questions? What am I forgetting? So, did you mention where you're grounding that?
We did mention that we've grounded the system. We have this connected to the BNC connector on the 850. That's a grounding point.
Yeah, so that's actually
Don't use
earth
this.
ground.
Don't do that.
Yeah, and so everybody has their own way of finding some way to ground. PASCO wouldn't let me make a little device that you plug into the wall to ground. So they said they'd never get past the regulators. And so normally what I do is either use this, or if you're not using the 850 for some reason, then you can use a power supply that has a ground and just plug the power supply in. You don't even have to turn it on and plug into that.
So, couple questions. Number one, regarding the gratings, a few people were asking if we sell the 600, or
Yes.
sell the grating by itself.
Yes, we do.
Yes, we do sell the grating by itself.
And then also, can you swap out the grating for one with like more finer?
Sure.
lines?
Yes.
But you're going to have diminishing returns because it's amazing how fine-tuned this is with the sizes of the slits that we put here and the sizes of the slits we put here. If we said, oh, well, let's just make it finer slits, it actually doesn't get you anywhere because our light sensor can only get, if you got a little tiny slit, your light sensor's not sensitive enough to pick up the light. Sure, it would give you finer, but it only gives you finer resolution in that you still have the resolution of 4,000 per turn on the rotary motion sensor and 60 to 1 ratio on that.
And if you do want to switch out the diffraction grading, remember what Ann said earlier about making sure that the diffraction side of the glass is against the plate so that the light goes through the glass and hits the diffraction grating before it exits to the focusing lens.
There is a little spot marked on the base to tell you where to put the focusing lens approximately. And the focusing lens is held down by neodymium magnets. And that follows the rule that every product that PASCO puts out has to have a neodymium magnet in it. Anyway, so that just sucks down to the steel plate here. And then you can easily slide it along and adjust it and make it perfect. So it's nice and crisp.
So you get beautiful data.
Yes.
We love beautiful data.
Yeah.
A few people commented, they said, thank you for the really nice description, the detailed description. But there is a question on the source of noise when you're doing the sweep.
Right.
What are the sources of the noise?
It's electrical. It is purely electrical noise, and we're just eliminating it by grounding it.
Would the system work with the PASCO photomultiplier tube?
The photomultiplier tube,
In place of the high intensity light sensor?
in order to do a different experiment, or
Not sure.
I mean, obviously, people have adapted this system to do nuclear experiments and use it as a goniometer for that. I've thought about adapting it for us.
All right. All right. Any other questions? Okay.
Okay,
I think we're good. We're going to get set up for the next experiment. So hang out. We'll be back in a couple minutes.
thank you very much.